So modulus is the length of a complex number. How long is it? If we draw it on the Eigen diagram, how far does it move from the point of origin? And so we've got the formula for you at the top there. The modulus of z is the square root of a squared plus b squared. Okay? So that's all it is. It's just Pythagoras theorem, isn't it? All right? If you've got, here's your vertical component, here's your horizontal component. What's the length of this? A squared plus b squared, square root. So if we have, this is z, our complex number, and we want to know the modulus of z, we're going to go the square root of the horizontal component plus, and we don't even consider the negative, all right, because we're squaring it anyway, so it gets rid of it. So it's root 3 squared plus 2 squared, which would be root 9 plus 4, root 13 units long. Okay? That's how far it stretches out on the plane. So with b there, if you were to find the modulus of z squared, you would first square it, and then find the modulus of it. But I'm going to skip that for now. For our proof, let's let z be a plus bi, and w be c plus bi. And we'll start with the left-hand side. Which will be a square root. So if we have the square, remember in surds, if we have the square root of m times the square root of n, we can write that as the square root of mn. Okay, any questions at this stage? No, let's proceed with it. All right, let's leave it there. Let's go to the right-hand side and see what we can do over there. So on the right-hand side, we've got the modulus of. Let's start by just finding ZW. Is A plus BI times C plus DI. Pause there so I can explain a bit of my thinking. So before we can find the modulus of ZW, I'm saying let's find the complex number ZW in its simplest form. And so I've expanded that out, and then I've isolated the real component and the imaginary component. And now that we've got both of them, we're ready to put that into the modulus formula. Okay? So if we're going to find the modulus of this, well, it's going to be, where should we go? I might come up here, so I've got a bit more space. Alright, so we're talking about the modulus of ZW. So that's going to be the square root of the real component squared plus the imaginary component squared. So here's the real component, AC take BD, let's square it. And the imaginary component is AD plus BC squared. Alright. So the real component squared plus the imaginary component. Now we're going to need to expand them, and then we're going to cancel some like terms. And we'll see we have the same thing. So we'll have AC squared, take 2ACBD plus BD squared. So yeah, that's an algebraic proof of it. It's just plugging it in, and then once we've processed the left-hand side sort of as much as we can, we jump to the right-hand side, we find ZW, then we say, well, what's the modulus of ZW? Process that, we see that they're equal. So therefore, this relationship is true, that the modulus of Z times the modulus of W is equal to the modulus of Z times W. So we've got all of those sort of properties listed there, and you're going to be proving some of them as well. Like you look at, we've got modulus of Z squared is equal to Z times the conjugate of Z. So that's what this exercise is a little bit about. Now, I will get you with this exercise. I don't want you to do it all because I haven't gone through the third example yet, and I won't, just for the sake of not overwhelming you. So we will stop, guys, at question 8. So you don't need to worry about 9 and 10 just yet.
Just yet.
Yeah. But if you can get up to 8 for homework, that'd be good.